specific questions about anything?
I don't know if you already went through it, but there's a question on a test that I kind of want to go through.
On the Chapter 7 test?
Mm-hmm.
Yeah, we can look at that. Do you remember which one?
It was the ones that had T's in it. Like, I know you have to use the, one of the, what's it called? I can't remember what it's called, but.
Question 4.
Yeah, that one.
This one? With T's in it?
No,
Or
the other one.
this one?
No,
With T's in
that
it?
one.
Okay. Yeah, cool. So we can look at one like this. Right, we're doing the Laplace transform with this. This is one of those questions where you can only solve this using Laplace transformation. You would not be able to solve this using the Chapter 4 stuff because of those T's in it. So just taking the Laplace of all of the terms, we can pull that 6 out of the second term. And the third term, too. Okay. So, we're going to be using multiple different of these things here. Of course, we're going to be using the derivative properties, but we're also going to be using this property down here as well. Anytime you are multiplying by a t onto a function, you end up taking derivatives. So, t times this second derivative, because that t is just to the first power, and then coming over here we're going to have negative 1 to the n, which is just negative 1. You know what we should do? Let's do scratch paper stuff. So let's just worry about this one thing here, just the Laplace of t in the second derivative. So it's going to be negative 1 to the 1, and then this is the first derivative with respect to s of the Laplace of whatever's left over, which is going to be the second derivative. But the Laplace of the second derivative is coming from this property here. So this is going to be the negative of the derivative of, and then the second derivative is s squared, the Laplace of the function itself, minus s times the function at 0, which is 4, minus the derivative of the function at 0, which is negative 5. So really that's going to be plus 5 on the end. But we're taking the derivative of this with respect to s, and it's the negative, so we'll leave the negative out in front, and let's just take the derivative of each of these terms separately. The derivative of this term, you're going to have to be a little bit careful here, because you're actually going to have to do a product rule, because both of these have s's in them. So it's the first s squared times the derivative of the second, we'll just write that as the derivative of the Laplace transformation, plus the second, which is the Laplace transformation, times the derivative of the first with respect to s, which is going to be the 2s. The 4 times s is going to have derivative negative 4, and then the 5 is just going to go to 0. So we're here, right? Now we can distribute the negative sign into all of that and make it look a little bit nicer. So negative s squared, it's going to be the derivative of the Laplace transform of y, plus 2s, and then just the Laplace transform of y, plus 4. Sorry, this is supposed to be a minus sign because you're distributing that negative sign. All right, this is what we're going to substitute just in for the first term. But we have to do the same thing for this other one. So moving on to that other one, the Laplace transform of ty prime, this is also going to be negative 1 times the derivative with respect to s, that's what this t is doing, times the Laplace transformation, or not times, but acting on the Laplace of the first derivative. The Laplace of the first derivative is s times the Laplace of y, and that's going to be minus 4, the function at 0. That's coming from this line here. Operating that derivative and the negative sign onto these two things, we still have the negative 1 out in front. We're going to have to do another product rule here. So first derivative of the second plus the second derivative of the first, and then this -4 is just going to go to 0. Distributing the negative sign into that, we get negative SL prime, and then minus L of y. Okay, now we can substitute all of that back into the original thing, just kind of see what we got. So back with the original differential equation here. The first term we're replacing with this, so negative s squared, derivative of the Laplace transform, minus 2s, the Laplace transform, plus 4. That's going to be minus 6 times this term, which was down here, negative s derivative of the Laplace transform minus the Laplace transform. That's going to be plus 6 times the Laplace transform. Oh, and I forgot to take the Laplace of the 24 on the other side. That was my bad. You do have to take the Laplace of this. You pull that 24 out, and then the Laplace of 1 is 1 over s. So this is going to end up being 24 over s on the end. All right, and then just cleaning all this stuff up and combining what we combined together, we can move this 4 over to the other side and then move everything else around. So the two terms that have the derivative are negative s squared plus 6x. That's on the first derivative of the Laplace transform. And then we have the actual Laplace itself, which has a negative 2s, a plus 6, and then another plus 6, so plus 12 on the Laplace. All right, that's just combining like terms with the derivative and then the function itself. Okay, and now we want to solve this for the Laplace transformation, which is kind of gross looking. This is now a linear differential equation with respect to the Laplace. So we have to get rid of this term by dividing it everywhere. On the right-hand side too. So just dividing everything by that negative s squared plus 6x. Now it's in that linear form. Now we have to find the, what was it called? The integrating factor. Multiply it on both sides and then yada, yada, yada. I don't really feel like going through all of this anymore at this point, because I promise you there's not going to be one on the final exam that looks like this. Well, I shouldn't promise that.
The only part that got me was when I had to take a derivative of it. I was trying to do something different.
Yeah, it's just using that property when you multiply by a t. How long is the final? I think it's 14 questions, but some of them are very short, like very short. I think there's 4 to 5 long questions on the actual exam. So is that okay enough for this one, knowing that you're not going to see one quite this big on the exam itself?
Yes.
Okay, cool. So just to show you what the actual answer would come out to be, like the answer is very simple. Yeah, that's true, right? But no, I try to make it so that the exam itself, the short questions really are short, like just a few lines to kind of get to the right answer. Anything else? Any other big questions? Otherwise, I was just going to jump into the final exam practice again, like we did yesterday. I think we made it up to 48 last time. Oops. Sort of. I just kind of arrowed through most of them. Out of the 47 or so that we went through, I think I actually solved maybe 15 to 20 of them, because there's so many on this practice one that are pretty identical. So I didn't go through every single one. But also you have to remember that in chapters 1, 2, and 3, like those really were short problems that weren't quite as involved as 5 and 7 and chapter 4 as well. But I just put that video up on Moodle, so if you want to go back and watch yesterday's meeting, you can go up and watch that now. Okay, so we'll just pick up, starting with this one here in 48. So just because you weren't here yesterday, the last thing that we talked about were these kinds of problems. This is one of those variation of parameter problems. You could not do that undetermined coefficients method to solve this. You have to do those V's to solve one like this. Same thing with this one. Because that t to the negative 8 is really in the denominator, you have to do the variation of parameters to be able to solve one like this. Then we jump into questions like this. You could, of course, do the Laplace transformation of this if you had the initial conditions, but you don't have the initial conditions here, so I guess we're stuck with doing it the normal way. Although it wasn't too bad when you had the equidimensional case, which is what this is. So t squared y double prime plus 6ty prime minus 36y is equal to 0. If you have equidimensional, which means you have a squared on the second derivative, a linear on the first derivative, and just a constant on the function itself, remember that what you want to do here is you want to use something called the characteristic equation. The characteristic equation is ar squared plus b minus ar plus c is equal to 0. And remember, the whole point of trying this is because we are trying solutions in the form t to the r. All right, so just plugging in our constants that we have into the characteristic equation. We have the a, which is a constant of 1, so just r squared. Plus b minus a, which is 6 minus 1, so 5r. And then minus 36 is equal to 0. Maybe this could be factored. It doesn't look like it, though. I'm going to go with no. I don't think that can be factored, so because it cannot be factored, we're going to have to do quadratic formula stuff. So negative b plus and minus the square root of b squared minus 4 times a times c. That's all divided by 2 times a, which is just 2. All right, and then cleaning this up, I'm probably going to need some calculator help here. Does anybody have a calculator with them? Does that come out to be anything remotely nice?
$169, so 13.
Okay, so we're going to have the negative 5 plus and minus 13 all over 2. That gives us two solutions. Negative 4 and something else. Negative 9? I think so. Okay, so we get these two. Oh, wait. Was this negative? No, right? It wasn't. We're good.
No, it's positive.
Okay, so we get these two solutions, and then that's pretty much it. That means that my solution for this equidimensional case is going to be a constant and then t to the first r value plus another constant t to the second r value. Oops. And that's it. So that's what you would type in here. Be careful with these equidimensional cases, because depending on the types of roots that you get, there may be some weird things going on. So either go back in your notes or make sure you have the book handy. If this is a double root, then you have to do something weird with a natural log. If this comes out to be a complex root, then you're going to have some weird cosines and sines going on here. I don't really remember exactly how they are. But just to show you that we got the right stuff here. There we go. I mean, my numbers are different because when I hit my cheating button, it changes my question, but it's the same thing. Okay, moving on. So here we have another one, same thing. Okay, cool. You'll also more than likely have questions like this on the exam as well. So this is kind of a word problem based on these second order differential equations and how they model a real life spring. So using the paradigm below, that means this equation here, where we have the inertia, just the mass, times the second derivative plus the damping constant, the first derivative, plus the stiffness times the function. That's just the normal equation for a spring. So using that, what are the inertia, damping, and stiffness for this equation? If y is greater than 0, what is the sign of the stiffness constant? Does this answer help the runaway behavior of this solution? So just to go through it, the inertia would be the mass. That's the coefficient on the second derivative, so just 1. This does not have any damping to it. So this one was kind of weird, right? I think we had one like this on the homeworks that you guys asked before. But we have the 7y squared here, which means the stiffness is everything except for one of the y's, so negative 7y. So if y is greater than 0, then the sign of the stiffness constant would be negative, right? Because you're multiplying a negative number times a positive number. Does this answer help explain the runaway behavior of this solution? And you can read through that, but the answer should be, yeah, it does explain why. It explains why because when you are to the right of the equilibrium, the stiffness is negative, which means it actually, this is a spring that never comes back to equilibrium. As soon as you move it slightly away from equilibrium, it just blows up to the right forever and ever and ever. So it's not a realistic spring. But anyway, you'll have questions like this where you're using the spring stuff to answer some kind of modeling questions. This wasn't as good of an example as I was hoping it would be. So maybe go back into that section 8 and section 9 homework for chapter 4 and look at some of those other questions that came out of this. What's really important from that section are those definitions, underdamping, overdamping, critical damping. Make sure you know those 3 and what that means. Is that all right? Does that make sense of what I'm looking for this last little bit of chapter 4 stuff? Any questions about it? Great. Thanks, Thomas. Distracted. It's okay. Go back and look at this stuff. All right, moving on. Chapter 5 stuff. So with the chapter 5 stuff, that's when you had these systems of equations. So remember when you're solving these systems of equations, you have to eliminate one of the variables by multiplying by one of these operators onto each of the equations separately, so that way something cancels out. So for this question, they're asking you to eliminate v and then solve for the remaining u. If I wanted to eliminate the v's of these equations, then they have to be the same operator. So for this first equation, it is missing the 4d plus 1. So I'm going to multiply the operator 4d plus 1 onto the entire first equation. So we're going to have 4d plus 1 and the d plus 3 acting on the function u, minus 4d plus 1, and then the d plus 3, that's acting on the function v. And don't forget to also apply that, that linear operator onto the function on the right-hand side. So we're going to operate 4d plus 1 onto the e to the t of the first equation as well. For the second equation, that one is missing the d plus 3. So I'm going to multiply all three terms of the second equation by d plus 3. Don't forget to operate that on the very last term of this one as well. Now, the reason we did that is if you add these two equations together, the operator on v is the same. Well, it's actually the opposite in this case for both of these equations. So I'm going to add these two equations together. That way, these two terms cancel each other out. When I do add the equations together, I'm going to be adding these u's together, and it's going to look kind of gross to begin with. So 4d plus 1 times d plus 3 plus d plus 3 times d minus 1, all of that acting on u is going to be equal to the right-hand side, 4d plus 1 acting on e to the t, plus d plus 3 acting on just 3. All right, now we want to clean this up and then solve it for u. To clean it up, we're going to distribute out these parentheses and combine like terms, and we'll go ahead and figure out what this right-hand side is going to be. First, multiplying all this stuff out, so just foiling these together. Foiling the other one together. That all acting on u. On the right-hand side, 4d acting on e to the t. Remember that this capital D just means to take the derivative. So this is going to be taking the derivative of e to the t and then multiplying by 4, which is just 4e to the t. The 1 acting on e to the t is just going to be 1 times e to the t. Then over here, the d acting on the 3 says to take the derivative of a 3, which is just 0. Plus the 3 acting on 3 says to multiply. 3 times 3 is 9. All right, adding and combining the like terms over here. Uh-oh, I goofed it up a little bit, didn't I? 12d plus d plus 3. That looks better. So combining the like terms, we have a 4d squared and a d squared, so 5d squared. I have a 12 plus 1, 13, minus 1, 12, plus 3, 15d. And then for my constants, I have a plus 3 and a minus 3. Those two things just disappear. On the right-hand side, I can combine some of this stuff together as well. Last little thing you want to do is to go ahead and finish up this operator here. So it's going to be 5u second derivative plus 15u first derivative is equal to that 5e to the t plus 9. Now, you want to solve this using whatever method you need to solve that. Unfortunately, right, there's two terms here, so we're going to have to do chapter 4 stuff, and we're going to do the homogeneous solution. We're going to have to do the undetermined coefficient solution for this one, and the undetermined coefficient solution for the 9 as well. So first, the homogeneous part. That's going to be looking at the auxiliary equation, 5r squared plus 15r is equal to 0. If you divide everything by 5 and factor a little bit, you're going to get r times r plus 3 is equal to 0, which gives us two solutions. R is 0 or r is 3, negative 3. Okay, that means that you're going to have the homogeneous solution of C1 e to the 0, which is nothing, plus C2 e to the negative 3t. So that's the homogeneous solution. Okay, that times the undetermined, not times, but added to, undetermined coefficient for the 5e to the t term. That's going to have a particular solution of just a e to the t. Right? There's no polynomials, there's no cosines or sines, it's just e to the t, and because there's just a constant in front, we're going to have a constant in front. But we have to take this and plug that into my differential equation here, which means that we need the first and the second derivative. First derivative of that is just a e to the t. Second derivative of that is also just a e to the t. So plugging that into here, we're going to have 5a e to the t plus 15a e to the t, and that's going to be equal to just the thing that we're trying to solve for on the right-hand side, just that 5e to the t. We can divide everything by e to the t here and then combine the a's together to get 20a is equal to 5. In other words, a is 1/4. So this particular solution is just going to be 1/4 e to the t. All right. We also have to do the undetermined coefficient for the other thing, which was the 9 on the right-hand side. This one we have to be a little bit more careful about. The reason we have to be more careful is because of this root right here of 0. This root matches the e that would have been there, right? There's like an e to the 0 that's invisible here, which matches this one. That means we have to add an extra t onto what we think the answer may be. So instead of just setting my particular solution to be a constant, we're going to set it to be a linear term instead. Then we're going to take the first and the second derivative of this. So the first derivative is just going to be a. Second derivative is just going to be 0. And we're going to plug that back into the differential equation up top here. So we're going to have 5 times the second derivative, which is just 5 times 0, plus 15 times the first derivative, which was a, and we're going to set that equal to the right-hand side, which is just 9. Cool, so just dividing that over, we get 9/15, and 9/15 is 3/5, I think. Because the b didn't show up here, I'm just going to ignore it. So we're going to let that particular solution be 3/5 t. Now we can combine everything together for my final answer. This was u and not y's. Remember that we had the homogeneous solution, which was c1, just c1, plus c2 e to the negative 3t, plus this particular solution, 1/4 e to the t, plus this particular solution's 3/5 t. So now just picking the one over here that matches all that, it looks like this one. Yay. Now that we have u, it's asking us to find v. You could go back through all of these steps, which would be awful, but doable. Or what you could do is that you could try to go back to your system of equations and then pick one of them and solve it for v. So that's definitely doable as well. I don't really feel like doing either one though. Is this okay, this system of equation stuff? Does that make sense how we got that answer?
Yup.
There would be 4 different constraints with this one. So if they did give you initial conditions here and you kept going, you'd have to solve for that stuff, right? So yeah, it's possible, and there may be questions like that. So if they do give you initial conditions, there may be 4 different unknowns that you have to find at the end. So that would just be taking u as is. You would take the derivative of this. Once you had v, you would do v and then the derivative of that one. So there'd be 4 different equations to plug initial conditions into. It would just take time, which I know sucks. Now let's see what else we got here in chapter 5. Here's another one. It's the same exact thing. It's just this time they don't have the operators written out already. You would have to figure out your own operators based on this. Skip that one. Same thing, right? Another operator. type question. This one doesn't look quite as hard. It's not as long, but it's the same setup. You would rewrite this using these D operators and then eliminate one to solve for the other. Do we want to see another one of these, or do we feel okay about these systems?
You can go through. Well, no.
You want to do this one real quick?
We can. Why not?
Okay. All right, so I'm going to write that as x prime instead of dx dt. So x prime is equal to 4x minus y, and then y prime is equal to x plus 4y. Remember, before you do the operator stuff, you want to get all of the x's together, the y's together, and then anything else on the right-hand side. So for this first equation, I'm going to write that as x prime minus 4x plus y is equal to 0. For the second equation, I'm going to write that as negative x plus y prime minus 4y is equal to 0. So just kind of in that, I forget what we called it, but like the general form of the system. Now we can introduce that D operator. So we have x prime minus 4x, which is the operator D minus 4 acting on x. That's just going to be plus 1 acting on y, since we only have the one y there, all equal to 0. Same thing down here, but now we have negative 1 acting on the x. And then we have D minus 4 acting on the y. Now what we need, right, is we need to do some multiplications. That way we can eliminate one of them. This question is asking us to eliminate the x values. If I wanted to eliminate the x values, what I could do is just multiply the bottom equation by D minus 4, and then I would have a positive D minus 4x on the first equation, and then a negative D minus 4x on the second equation. And then I can just add the two together. So multiply second equation by that D minus 4. So I'm going to leave the first equation alone, not even mess around with that one. But on the second equation, we're going to multiply that D minus 4 onto there. I'm going to write this as D minus 4 all squared acting on the y. I don't have to worry about operating D minus 4 onto 0 because anything operating on 0 is just going to be 0. Okay, so now we can add the equations to make the x values disappear. Just adding the y values together, we're going to have a 1 plus that D minus 4 all squared. That acting on y, and just 0 on the right. So cleaning this up a little bit, foiling out D minus 4, that's going to be D squared minus 8D plus 16 acting on y. Combining the like terms together, we're going to have D squared minus 8D plus 15 acting on the y. At this point, we want to get rid of these operators and just go back to the regular form. D squared acting on y is the second derivative of y minus 8, and then D acting on y is the first derivative plus 15 acting on y is just 15y is equal to 0. Now we solve this however you want to solve it. Of course, to solve this is when we would do auxiliary stuff. So r squared minus 8r plus 15 is equal to 0. That looks like it could be factored. That factors into r minus 5 times r minus 3, which is really nice. So that gives me two solutions, 3 and 5, which means that we're going to have a solution of t, c1 e to the 3t plus c2 e to the 5t. All right, and you just pick the one over here. Oh no, they don't match any of them, do they? I must have made a simple mistake somewhere. Where's my mistake? It's probably way at the beginning, knowing me. Oh, right there, right? So the 1 and the 16, that actually adds to be 17, not 15. That means that we could not do something so nice. And we're going to have to do quadratic formula stuff. So just real quick, quadratic formula, 8 plus and minus the square root of 8 squared minus 4 times the c. That's all divided by 2. I need some calculator help again here. I'm guessing that's just 1, but maybe double check. Or maybe it's 4. So that's 69? Or 68, I meant.
It's 4. It's negative 4, though.
Okay. Yeah, so that's going to be a 2i, which means that we're going to have, on dividing each of them by 2, 4 plus and minus I. That means that we're going to have the solution that looks a little bit more complicated. C1 e to the 4t cosine of t plus C2 e to the 4t sine t. All right, so whichever one of those match over here. There we go, this one. Well, it was a good thing this one was multiple choice, right? I thought I goofed it up. But now that we have that one, now we can go back and solve for the y, or sorry, for the x. Because this one's a little bit simpler, I can show you how we would solve for the x. From these two equations, we would want to pick the one that's easy to solve for the x, and I would pick the second equation here. I could rewrite that as just x on one side and then y prime minus 4y by subtracting the 4y over. I have what y is equal to. I would just need to find its derivative to be able to plug that in. All right, I give up. But you would take the derivative of this, which would just be some product rule stuff. Plug that in for the first derivative, minus 4 times the function itself into the second derivative. I don't feel like doing those product rules right now because we're limited on time. But is that okay? Does that make sense going through this question? Awesome. Okay. Moving on. Let's see what else we got here in chapter 5. So you'll have questions like this as well. Convert the given initial value problem into an initial value problem for a system. So anytime you have these second order differential equations, you could rewrite them into just a linear system instead of dealing with the second order stuff. So it kind of starts you off right away here. Let x1 equal to y and x2 equal to y prime. Complete the differential equation and initial conditions for x1. So remember, x1 is y, so we're just going to leave that as y. X1 at 0 would be y at 0, which is 2. Oh, right, they don't want us to write it like that, I forgot. They want it in terms of the x1 stuff, right? So, and it's the derivative. All right, I was going too quick. My bad. It won't let me delete my answer. It's stuck there. There it goes. All right, sorry, slowing it down. x1 is equal to y, but we want xy prime. If I take the derivative of the left-hand side and the right-hand side, x1 prime is just y prime, but y prime is equal to x2. So x1 prime is the same thing as x2. Then it wants to know what x of 1, just the normal function at 0 is. Well, if x1 is y, y at 0 is 2. Okay. Okay. And then the second thing, so complete this one, x2 prime. Well, x2 prime is x2 here, prime, which is going to be the derivative of the right-hand side, which is y double prime. But y double prime is given to us up here. Y double prime is all of this stuff. But we have to be careful because we want to write this stuff in terms of x1s and x2s. So this stuff is going to be negative 4 sine of t minus y, but don't forget y is x1. plus 6 times y squared, which is x1 all squared. All right, and then it wants to know what is x2 at 0. Well, x2 is y prime, and y prime at 0 is negative 1. Great. So what we've done, right, is we've changed one second-order equation into two linear equations, or first-order equations. Just makes it a little bit easier to solve. Okay, moving on from that. Here's just another one. It's just that this has a bunch of different stuff. So here we have a system of second-order equations, and we're going to change it into 4 first-order equations. I don't feel like going all the way through that one, though. All right, so questions like this, I think most people had these all right. So this was just finding the critical points, and we used the critical points for those phase lines. So just set these two things equal to 0 and solve for the x and the y. That's not too bad. And then we're into chapter 7 stuff. Do we feel okay about chapter 7 stuff? I mean, we did just take a test on it.
Yeah, I already had my question answered. That first one, only one that was like.
Okay. I think there's maybe 2 or 3 questions from chapter 7. One long one, but the other 2 are going to be questions like this. So here they're just asking you to find the Laplace transform of this. And that takes a few minutes, right? Just using this table here. The other shorter question would be the other way around. So instead of asking you to find the Laplace transformation, they would give you the Laplace transformation and then ask you to find the inverse. I must have missed it. Or maybe there wasn't one on here. Oh, well, yeah, so there's going to be one like that on the test as well, where you have to find the inverse Laplace transform instead of finding the whole thing. There may also be a question like this, where it's asking you to do the whole thing, but I'm not actually expecting you to go through the whole process. I'm just going to ask you for what the Laplace transform is for the answer, and not the inverse Laplace transform, which is what takes the longest. So look for those. Okay, cool. But that's the chapter 7 stuff. And that's it. We made it all the way through the final exam practice. Valerie, you feeling all right about the exam next week?
We'll see. It's just you said mainly it's going to be over chapter 4, right?
The majority of questions are coming from chapter 4. Yeah, sorry, Thomas.
Okay.
And a lot of those questions are from the earlier stuff in chapter 4 even. So just to kind of go back to remind you, stuff like this, right, where you have a homogeneous equation and you just have to write out the homogeneous solution. Of course, there will be longer ones, like maybe not like that. Let's see if I can find a good one. Maybe like this, right? So where there is an external function on the right-hand side and you're using that method of undetermined coefficients.
Right.
Just make sure you're reading the question carefully. Like this one's only asking you to find the particular solution. It's not asking you to add the homogeneous solution onto that to find the general solution.
So you just do the A, or the coefficient thing, or?
Yeah, so this would be the A sine 7t plus B cosine 7t. And you'd plug that back in to find the A and the B.
That's easy enough.
Yep. Anything else, Thomas? You got any other big questions?
That's it. I am good. I'll just go and watch your other video over that first half, and then.
Yeah, there's 2. Well, I think there's just the one. There's just the video from yesterday. The video 2 days or 3 days ago, I think, was just chapter 7 stuff. But don't forget that you can go back to any of the other meetings that we had as well that you may have missed. All of that stuff is in Moodle. So I would play it to the dates. Like the chapter 5 test we took was April 22nd. So maybe a meeting or two before that one, look for the chapter 5 stuff. Same thing with the chapter 4 test. So the chapter 4 test was April 1st. So maybe the week before that, if you really want like some hardcore chapter 4 review, look to those meetings.
Okay, makes sense.
Yep.
Thank you.
Yep, of course. Thomas, that's a good point that the first 3 aren't going to have any videos. Although yesterday, I did a lot chapter 1, 2, and 3. So watch yesterday's video for chapters 1, 2, and 3 review. But other than that, yeah, I don't think there's any videos for those.
And that was just like the separable ones and the ODE.
Yeah, and then there was the linear ones as well. The integrating factor ones was in this stuff.
Okay, yeah. I think I remember most of that.
Mm-hmm. And then a few word problems were in here too.
Oh yeah, the mixture problems.
The mixture problems came from this stuff. Yeah.
Okay.
There's not going to be a lot of videos from chapter 4 except for the very end, because I think that this all started the week before we went to take the chapter 4 test. And I think we did some meetings right before the chapter 4 test, although don't quote me on that. Maybe we didn't. Maybe there's not any videos on chapter 4. I just don't remember. You're just going to have to go back and look in your notes in class and go back and look through these homeworks. And then again, the video yesterday, I did some chapter 4 stuff, like half of it. The last half of it we did today. Okay. Great. You